let's look at combining all the transformations at once. Remember there was a certain order in which you had to do algebra? That is, you had to always go brackets, exponents, division, multiplication, addition, and then subtraction. And similarly, with graphing, we have a certain order. We do our expansions and compressions first, then our reflections, and last of all, our translations. So expand and compress, then reflect all the negatives, and translate. That is the shift up, down, left, right. So for a question like this, then the 2 in front, because it's outside the function, is giving you a vertical expansion by a factor of 2. The negative, y goes to minus y, it is reflecting it across the x-axis. It's going to look upside down. This minus 1 is outside of the root function. It's going to shift it 1 down. The plus 3 is inside the root function, which means it's going to give us a horizontal shift, not of 3 in the positive direction, but 3 to the left. So you know what the graph of square root x looks like. Square root of 0 is 0, square root of 1 is 1, the square root of 1, 2, 3, 4 is 2, the square root of 9 is 3. This is what your root function looks like. So we are going to do all those transformations to it. So remember the mapping. If I've done those transformations to the function, I would have taken any point xy on the original over to the point x minus 3, that would move it to the left, and negative 2y minus 1. The negative 2 would expand it, reflect it, the minus 1 would shift it down. So in order to get this graph then, I'm just going to use key points. So key points here, 0, 0, 1, 1, 4, 2, and 9, 3. And if I put them through that transformation, you're going to see that the point 0, 0 would that's hard to see, would 0, 0, still hard to see, would transform over to 0 minus 3, negative 2 times 0 minus 1. So it's going to go over here to the point negative 1, 2, 3, negative 1. And then the point 1, 1. Well, it's going to transform over to 1 minus 3, and 1 times negative 2 is negative 2 times negative 1, or subtract 1, gives me negative 3. So negative 2. Okay, so rather than going this way, remember this is flipping upside down and going this way. I'll get one more point in there. So if I took the point x is 9, y is 3, well, it would go to the point x is 6 and y is negative 7. Okay, so down like that. Okay, so there's all the transformations combined into one on a radical function. So then let's see what happens with a rational function. Okay, so here's our rational function. 1 over 2, bracket x plus 1, and then plus 2. Okay, so remember what a rational function looks like. It has 2 branches to it. So if I were to graph the function y equals 1 over x, I would have a vertical asymptote where x is equal to 0, and I'm going to get a horizontal one along the x-axis as well. So what's happened here is I've got a horizontal compression of a half. I've got a shift of 1 unit to the left and 2 units up. So just to make this kind of easy, I'm going to take and I'm going to move my asymptotes, because the asymptotes, the equation for both of them is 0. Y equals 0 for one asymptote, x equals 0 for the other asymptote. So this horizontal compression, multiplying it by a half, either way, is going to still give me 0. The only thing that's going to move it is the horizontal one will move when I put it 2 up. And the vertical one will move when I move it, shift it 1 to the left. Okay, so here are my asymptotes at x equals -1 and at y is equal to 2. And then you should be expecting this to look kind of the same as the original function with that horizontal compression of a half. Let's do the mapping and look at what happens to any point x, y on the original function. So it's going to go to 1/2 x minus 1 and y plus 2. How come that 2 is horizontal? We'll look at the original function. Because it's in the denominator, I've replaced the x with 2x plus 2. And then because of the order of operations, I have to factor out the leading coefficient on the x. Okay, so I know one point for sure on this graph. It's this point right here. If x is 1, y is 1. And another point right here. If x is -1, y is -1. So I'm going to take this point 1, 1, and I'm going to put it through the mapping. What happens to it? It becomes a half subtract 1 and 1 plus 2. Okay, so x is -1/2 and y is 1, 2, 3. Okay, so right here, and I'm going to just give a quick sketch of that reciprocal function. The point -1, -1 would move 2. See, -1 times a half is -1/2. Subtract 1 is -1.5, or -3/2. I put a -1 in for y, and I get 1 instead. So x is -1.5 and y is 1. There's my starting point for the other branch of that reciprocal function. Okay, so combining those transformations. Okay, let's try it with a trig function. Oh, come on, give me the equation here, people. Where do we got? Okay, so that -3 is giving us a vertical expansion. And remember that you need to factor out the 2 inside of the brackets. So I have y is equal to -3 times the sine of 2 bracket x plus pi by 2, close all your brackets, minus 1. Okay, so we've got the -3 is giving us a vertical, I see what I did wrong. The -3 is giving us a vertical expansion of 3, and the negative, y goes to minus y, is reflecting it in the x-axis. So flipping our sign upside down. This 2 inside the function is giving us a horizontal compression of a half. So the period for the sine function won't be 2 pi. The period will only be pi. Plus pi by 2, that is going to give us a horizontal shift of pi by 2 to the left. And the minus 1 is moving the whole thing 1 down. Okay, so let me try to zoom this in for you, and we'll try to do that graph. Okay, so first of all, let's realize that we have an amplitude of 3. So my amplitude is equal to 3, and my displacement is -1. So it's like I'm taking and centering. My central axis is right here at -1. And from here, I'm going to go up 1, 2, 3. Here's my maximum value of 2. From my central axis, I would go down 1, 2, 3. Here's my minimum value of -4. Okay, so my function is going to cycle in between 2 and -4. All right, then so that gives us our vertical axis, all of the important things for vertical. So we got to graph our sine function, and we got to keep it in this range between 2 and -4, and the center of it is there at -1. So we're getting that from the amplitude and displacement. Here's the hard part. It's labeling the x-axis. So look at the shift and the period. And I think a scale of π/4 would make all of this really easy. So if this is 1 π/4, this would be 2 π/4s. Reduce the fraction. This would be 3 π/4, and then this would be pi. So if I start at π/2 to the left, I would be starting at 1 π/4, 2 π/4, that's a π/2 to the left. Remember, sine starts on the central axis. Also remember, I asked you to graph a negative sign. A positive sign starts at the center and goes up to the top and then back to the center and down to the bottom. A negative sign starts at the center and goes down to the bottom. So we're going to graph a negative sign. So it is starting at the center on the central axis, π/2 to the left. It's starting here. The period is pi. So from this point, count 1, 2, 3, 4 π/4s. That's 1 pi. The length from here to here is the period of the function. So between these 2 points, I need to complete 1 cycle of my negative sine graph. So divide it into 1, 2, 3, 4 equal parts, and then let's do it. So I'm going to start at the center. It's negative sine to the min, to the center, to the max, to the center. There's 1 cycle, and of course, now that we've got our pattern started, we could just keep on going to the min, to the center, to the max, to the center, to the min, and keep graphing your function. Okay, so the important thing there was to remember to factor out that 2, and let me just write a couple of other things in here for you. So remember that we had this formula for a sine function. Y equals A times the sine, square bracket B, round bracket, x minus c, close all the brackets, plus d. So the A was giving you the amplitude, and the amplitude is the absolute value of the max minus the min divided by 2. Absolute value, even if the A is negative. The negative means the reflection. When we're asking for the amplitude, I'm asking you the height of the wave. It's a distance, so it's always positive. The D is your displacement. It's like the center or like the average. And to find an average, you just take a max, add the min, and divide by 2. Okay, the D can be negative. it just was in the graph we just did. Okay, so the A and the D affect the vertical component. The B and the C affect the horizontal component. The B value tells you the horizontal compression or expansion. I've got two formulas for you. B is equal to the normal period of your sine graph, 2 pi, divided by the period of the one you were trying to graph. So B is 2 pi over the period, or rearranging this, if you're looking at a function, the period is 2 pi over B. Of course, C is giving you your phase shift to the left or to the right. Okay, sometimes you need to change the form of an equation before you can graph it. So graphing this quadratic equation, much easier to do if you have it in your standard form, which means you need to complete the square. Okay, how fun is that? So let me remind you how to do that. Y is equal to, factor out the leading coefficient, and you've got x squared. Factor it out of the negative 6x, and you've got plus 2x. Close your brackets, leave the 8 outside. Now you have to remember, what's your magic number? So look at your middle term, divide it by 2, square the answer. Magic number is 1. You're going to add it, and because you're not just allowed to change anything, you're going to take it right off. Okay, so we are trying to create a perfect square trinomial when we're doing that. There is a perfect square trinomial. This -1 isn't helping things. Let's get rid of it. But when you get rid of it, remember that this leading coefficient has to multiply that -1. So I'm going to take the -1 and multiply it by -3 as I kick it out of the brackets. So I've got this. Y is equal to -3, bracket, x squared plus 2x plus 1, my perfect square trinomial. And outside the brackets, I've got -1 times -3 plus 8. Let's complete the square. I've got x plus 1 all squared, combined like terms. This is a parabola with a vertex at -1 and positive 11. It opens down because of the negative in front of the leading coefficient, and it has a pattern. Remember the pattern for a parabola? Up 1 over 1, up 1 over 2, over 3, up 1 over 5. I'm saying it backwards. Over 1, up 1, over 1, up 3, over 1, up 5, over 1, up 7. We can do this. So here's my pattern. That leading coefficient, -3, is going to make this my pattern. So starting with the vertex at -1, and 1, 2, 3, 4, 5, oh my gosh, let's go 2, 4, 6, 8, 10, 11. So right here, then I would have to go over 1 and down 3, and over 1 and down 9, and graph my parabola. All right, absolute value functions. So y equal, oh, and this one's a little bit more intense because we're not just taking the absolute value of a number, we're actually taking the absolute value of a function. So if I'm graphing y equals the absolute value of f at x, oh, hold on, then the part of the graph of this original function that's above is going to stay the same, and the part below is going to reflect over the x, above the x-axis. So for example, if I sketch x squared minus 1, you guys all know what that looks like. It looks like a parabola that opens up and has a vertex at 0, -1, and follows the pattern over 1, up 1, over 1 up 1, 2, 3, and over 1 up 1, 2, 3, 4, 5, and keep the symmetry. Okay, so it looks like this. Okay, so I have function composition here. I am going to take the absolute value of that whole function. Okay, so when I take the absolute value, the part that's above is going to stay above. Okay, so that stays there. The part that below is going to flip up. So in pink is the absolute value of that parabola. Similarly, with the cos of a function, then if I graph cos x, and let's just say my scale here is pi by 2, and let's make that 1 and that -1. Then cos starts at the top, to the center, to the bottom, to the center, and back to the top. And let's go backwards here. Okay, so I'm going to graph 2 cycles of cos. Now, if I graph the absolute value of it, then all the parts that were above would stay above. All the parts that are below will reflect up. So now my cos graph looks like this, but I want to graph the negative of that. And when y goes to minus y, I reflect this down over the x-axis. So my final graph is the one that you are seeing here in green. Okay, when you're using your graphing calculator, you'll need to work with the viewing rectangle. So make sure you can set your windows up properly so that you can see all parts of the graph. So we would want to see the maximum, the minimum of the vertical, the minimum, the maximum of the horizontal. You'll often see it written this way: square brackets AB by square brackets CD. So the AB are like what values you left for the X, and the CD are like the values you left for the Y, aka you got the domain by range. Okay, so let's just do a little bit of practice. What's an appropriate viewing rectangle for this function? Well, you need to know what the domain of this function is. And the domain of this function, because it's a radical function, means that what's underneath that has to be positive. So calculate your domain. 8 minus 2x squared has to be greater than equal to 0. Let's set it equal to 0 and then just do an interval test. I'm going to factor out a 2 and I get 4 minus x squared. This would be 0 if x squared were equal to 4. That is, if x were equal to plus or minus 2. So here's -2, here's +2. Okay, I know that I can take the square root of 0, so -2 and +2 are both in the domain of that function. The question is, what part of those intervals do I want? So just test it. Let's start here in the middle, a number in between -2 and +2, a number like, let's say, 0. If I put 0 into this equation, would it be bigger than 0? So if I put 0 in, I'm going to have 8 minus nothing. It would be 8. So this part of the interval will work. If I put a number over here, like let's say I put 3 into the domain, I would have 8 minus 2 times 3 squared. 3 squared, 9 times 2, 18. 8 minus 18, I'd get -10. That's not going to work. and you can talk it through for yourself, but it's also not going to work over there. So the domain for my function is from -2 to +2. And so when you're graphing it, set up your viewing calculator, your viewing window from -2 to +2 for the x values. And then what's the biggest this could be? Well, can you see that if you're taking the square root of 8 minus 2x squared, this is going to reach a maximum when you subtract the smallest number off, and the smallest number you can take off of here is going to be 0. So the most this could be is root 8. My range is going from 0 up to the square root of 8. How do I know 0? Well, what happens if I put -2? Well, I'll tell you why. Because you're taking the square root, and a square root can never be bigger than 0, can never be smaller than 0. So 0 is the smallest value you're going to get out of that. Okay, so if you set this up from 0 to root 8, you're going to see the entire graph in that viewing rectangle. If you're sketching the graph of x cubed minus 150x, you should know that this is a cubic function, and it could possibly look like this. So the largest number the largest number of, I don't know why it's doing that, I do not want that text, of x-intercepts could possibly be is 3. Okay, so let's take this and take out the GCF. I'm left with x squared minus 150. Okay, so that allows me to see that I have zeros for that function when x is equal to 0 or plus or minus the square root of 150. So when I graph this, I need to see those 3 roots. Here's one of them at 0. Here's one of them at the positive root of 150. Here's the other one at the negative root of 150. Okay, I'm trying to get too close to that. I'm not going to write it. Okay, so make sure that your window at least includes that smallest root and the largest root. Then your y values, I'm going to tell you what they are for right now. -710 and +710. Set your window up like that, and you will see the entire cubic and all of the key points to it. Okay, of course it keeps on going outside your window, but you've seen all the important pieces of it. Okay, and then let's graph this function y equals 1 over x, our reciprocal function, 1 over 1 minus x. Okay, so of course we know what the graph of y equals 1 over x looks like. Looks like kind of like that. And we've got some key points, 1, 1, and -1, -1. Before we start, let's write this in its proper format. Factor out the leading coefficient. So you have the graph of -1 over x minus 1. You're taking this graph 1 over x. The negative is going to reflect it over the x-axis, that is, flip it upside down so that it looks like this instead. And that -1 is going to shift the whole thing 1 to the right. So my domain and range for this function are all reals except x can't equal 1. That's the domain for this function, so I for sure want to see that in it. So when I graph this, I know that I'm going to have a vertical asymptote at x is equal to 1. And then I'm going to take and I'm going to do a mapping with this. Oops. So that mapping would take any point xy on the original over to the point x plus 1, because I'm shifting it 1 to the right, negative y. So the point that was on the graph 1, 1 is going to become the point x is 2, y is negative 1. And then it's going to look. There's one branch. The other point, negative 1, is going to become the point 0, 1. And here's the other branch. Because, of course, I didn't put it in here, that you do have a horizontal asymptote, right, that you never moved. Okay. If we're graphing a cube root, then just going to go over this quickly. A cube root graph is going to look like a cubed graph flipped over because it's an inverse. It's defined for all reals, and the range is all reals. So just give it a little bit of space on your window. Okay, if you have to find solutions and pay attention to how many decimal places, then you're setting these equal to each other and finding where they intersect. That is, where does cos x equal x? We'll graph cos x in your equation editor as y1, graph 1 in your equation editor for y2. And you're going to see your cos graph doing this, and the line y equals, oh, sorry, that's not a 1. It's an x. And then you're graphing the line y equals x, and then you need to see where they intersect. Okay, so our window. I want to see a cycle. I'm going to look at 2 cycles of cos. So from negative 2 pi to positive 2 pi. And I'm going to make sure that I can see from negative 5 to positive 5, although I know that my cos graph goes from 1 to negative 1. My y equals x can just keep on going, so that should show you everything. You're looking for the intersection, so using your calculate menu, you should be finding that intersection when x is equal to 0.74. Of course, at that point, y is also equal to 0.74 because you've got the equation y equals x for your second. Okay, so some fun homework for you to start on right here, and we'll talk again later. Bye-bye.